Assalamualaikum warahmatullahi taala wabarakatuh, and a very good day to all panelists, Associate Professor IR Dr. Amir Radzi bin Abdul Ghani and Madam Fauziah binti Md Yusof, and to all viewers of this video presentation. My name is Raja Muhammad Amiril Isyraq bin Raja Azmy from Faculty of Mechanical Engineering. Today I would like to present my final year project 1 proposal entitled Structural Integrity Evaluation on Hydraulic Folding Crane. This project has been supervised by Professor Madya, Ahmad, Kamil, Husaain. I'm going to start my presentation with the summary of this project. Firstly, have a look at the project summary. Due to the limit of human energy power, development of this equipment can overcome the problem in handling heavy things. It uses a heavy cantilever support structure to hold the engine in the mid-air, so that the mechanic can carefully connect or disconnect fragile hoses and wires on the engines to the frame of the vehicle. So the aim of this project is to evaluate the structural integrity of hydraulic folding crane, besides to identify at what condition of the critical stress that will be applied on the certain part area. The package that will be used in this project is by using CATIA to remodel in order to implement a finite element analysis on the selected part. Then we go through to the introduction. Hydraulic folding crane are a common type of crane that are frequently seen in places like mechanic workshop and car repair shop. It also can be separated into several parts for storage and is easy to fold. The hydraulic cranes clearly can achieve a great amount of power with a small applying force. There are some variants to all these tools, as they are not created equally and have different design, dimension, size, and capability to accommodate the weight of engines. Besides increasing the productivity for manpower, it also can manage to reduce the injuries that may occur to operator. We go to literature review. The lifting machine has advanced through numerous eras and times since the late 6th century BC, when ancient Greeks built the first crane for lifting such a great weight. During the Roman Empire, when building and construction reached tremendous proportions, the crane was at its peak. As a result, the Romans adapted the Greek cranes and improved upon them. Then, cranes and hoists from the Middle Age, as opposed to current cranes and hoists, much like their counterparts in Greece and Rome, were primarily capable of vertical lift. During the Industrial Revolution, the first modern crane for loading goods were developed at ports. Sir William Armstrong, an industrialist and businessman, created a hydraulic water power crane in 1838 that was employed as a ram enclosed cylinder that was pushed down by pressure fluid entering the cylinder. As a result, the cylinder's valve controls the amount of fluid intake in relation to the crane's load. Then we go to the capability of the crane. For capability of the crane, engine cranes are usually made of heavy-duty metal and can lift loads up to 4 tons. A smaller engine cranes can lift up to half ton, whereas larger hoists can lift up to 8 tons. Engine cranes can be utilized with nearly any car engines because the majority of today's car is for V4 and V6 engines, which do not exceed the 2 tons weight constraint. The Warrior foldable work engine crane, for example, is currently on the market and has a weight capacity of either 1 ton or 2 tons, making it suited for various heavy-duty operations. Meanwhile, the PFAFF Silver Blow 500 kg V-shaped HWK KLS folding engine crane has half tons weight capability for a smaller crane. For material selection, First part are the vertical columns and base where the compressive force is concentrated on the vertical column. As a result, cast iron was chosen as the material for the column since it has superior casting, can endure high compressive stress, and is without doubt inexpensive. Also, the primary elements are made up from carbon and iron with content percentage of 1.7% up to 4.5%. Secondly, is the adjustable and extended booms. The material utilized to construct this component must be robust and durable due to enormous load given to them. Hence, the best material selection for this material is structural steel, which contains carbon element up to 1.5%, which resulted in increased hardness and strength. Next are the hook and chain. Because this component is subjected to a lot of tensile stress, rough iron is the best material to select because it's malleable, robust, and has a lot of flexibility. Also, it has carbon content of 0.02%, 0.12% silicon, 0.018% of phosphorus, 0.07% of slag, and the rest are made from iron. And lastly, bolts and pins, where the material used is subjected to tensile stress and shearing stress. As a result, my steel is the optimal material for these parts to meet the standards for resisting these loads. Then we go to the problem statement. There are plenty of failures possibility that may occur if the equipment is not handled properly as followed by procedure. For example, the optional choice to extend the boom into desired length does not match with the required weight and size of the engine, which can consequently make the crane to flip over or unstable. Furthermore, the attachment between the hook and engine are not in symmetrical axis, where it can cause the engine load stress cannot be distributed uniformly, which provide extra stress at certain area that shorten the lifespan of the equipment. Also, common area space for a car repair shop or another average workshop is mostly not suitable to be used for overhead crane or transport the heavy duty component using a forklift. Then we go to the main objective of this research, which is to evaluate the structural integrity of typical small hydraulic folding crane that is commonly used in car repair shops using finite element analysis. Next, the purpose is to help the engineer to understand the distributed force applied by loads on the equipment and justify the performance of structure by investigation of the internal stresses. Lastly, the local high stress area in the structure will be identified by selecting 3 critical parts of the model structure for further development and evaluation. We are going to the scope and limitation. In this project, the structure to be researched is a folding crane that has a carry large load up to 2 tons. This crane has 2 side bars that are connected to produce 2 links and pin joint connected with the base. Using a proper bolts connection, the vertical column is fixed on the welded cross that form the base. The selected crane has 6 wheels, 4 of them are located in the front and the back ends, while the other 2 are located beneath the vertical column that connects the boom and the piston cylinder. Because the crane is hydraulic, the engine waves are lifted and project work modeling should not be overly complicated, then should not be simplified more than the study's actual functioning. A model structure of the chosen folding crane is included during the modeling. Then we go to the methodology, where the procedure starts with identifying the problem and then move on to conducting a literature review to fulfill the extent of limitation and specification. When the demand has been narrowed down to a more particular scope, the hydraulic folding crane is modeled using CATIA software with the proper dimension. Following that, the critical parameters should be established to ensure that the chosen equipment can withstand high loads. As a result, using von Mises analysis, the study is done to forecast and estimate how much stress is applied to the specific area so that improvement can be made in future research. At the end of the process, the parts were examined to see if they meet the requirement for the loads accommodated and will not collapse over time. As a result, all of the data was saved for future development and review. Then we go to the expected result. The full assembly of modeling crane is expected to be obtained as a result of this project, which consists of combination of different parts that have been modeled separately, including the main body frame, adjustable boom, extended boom, hydraulic piston, support bar, wheel, and bolt and pin connecting joints. The dimension used for each part where it can meet the requirement and tolerance at the connecting region is the major consideration for assembly process. Also, by utilizing von Mises stress analysis, specific section will be studied on 3 selected elements that consist of adjustable boom, hook, and main body, as it was projected to provide a potentially crucial part from the entire assembled model structure. The factors or parameter involved with the stress, including length from the wake, are attached. Then we go to the last part, which is preliminary outcome, where stress analysis was important to understand the behavior of the structure when a load is applied to it. Von Mises stress analysis becoming a parameter in order to compare strength between different design and parts of the hydraulic folding crane. The structural integrity evaluation is a method to verify stress in the structure when it is subjected to load. The selected part experienced a complex loading when the body had normal stress and shear stress. The von Mises stress boiling all the complex stresses into scalar number. Then the load is constant distributed force, which is set at initial of 1000 kilograms, which equivalent to 8800 newtons downward in the z-axis, and the result can be seen in all figures above. That's all for me. Thank you.